Okay, so before we start today, does anybody have any questions for me? Yeah.
For the assignment, the very last question,
Yeah.
taking 5 drugs simultaneously, what are you asking?
So, two things. So the question is the very last question on the assignment, which is 5.4 maybe. So two things I want to say about that. So one is, this is a question that's very hard in general, so do the best you can. In fact, it's a field of it's part of a field of combinatorics called combinatorial designs. But the question is basically the following. You have 21 things and drugs, different drugs, and you're worried about bad interactions that happen between 3 of them. So when you take 3 particular drugs at a time, maybe you get sick or maybe you die. So the number of triples of 21 drugs is 21 choose 3. And you would like to test, you think that these 21 drugs are all safe in the sense that I can take any 3 of them at a time and not get sick. And you're willing to test that by taking some poor test subject and feeding them 5 drugs at a time. And then if they die, you conclude, there must have been 3 of those 5 that killed them, so that's not a safe set of drugs. And you want to do this, so you keep feeding this poor person 5 drugs at a time. They survive or they die. Assuming they survive, the next day you come, you give them another 5 drugs. The next day you give them another 5 drugs, assuming they live the whole time. So that by the end of it, this person has taken every combination of 3 drugs they've taken at one sitting. So that means one experiment lets you test 5 choose 3 triples. If I give this person 5 drugs, well, the number of triples among that 5 is 5 choose 3, that's 10. So that's like, ideally, with each experiment, one day of giving this person 5 drugs, you have tried out 10 different triple interactions and verified that they're safe because this person had all those triples in them at once. So the question is, how many of these kinds of trials does it take before you have tried every triple of drugs?
So you're still feeding the subject 3 drugs at a time?
No, you're feeding the subject 5 drugs at a time. What you want to make sure is that at the end of the whole process, if you specify any 3 drugs, there was one time that person ate those 3 drugs at once, including and 2 extras on top of it. So that is the last question on the assignment for a good reason. It's a hard one, so I won't offer you much advice on how to tackle it, but do the best you can. And remember that these assignments are graded. Each question is worth exactly the same amount. So if a question takes you 20 hours, it will be worth exactly the same amount as a question that takes you 2 minutes. So start with the questions that take you 2 minutes. Other questions? Yeah.
Does it matter what order we solve the question in? Like if we reference other questions to solve other questions?
For the sake of keeping the TAs happy, who ultimately assign your marks, you should present your solutions in the order that the questions appear on the assignment.
So for example, like if I were to use question 9 of deck strings to solve 7 and 8, that would be like not encouraged.
No, I would like to, yeah, so some of them are, for example, do this for the case k equals 1, answer this for the case k equals 2, and then answer this for the case of general k. I would like to see the solution for the case 1, solution for the case 2, and then the solution for the general k. For your own benefit, you can work the other way and make sure that once you find the solution for the general value of k, that it gives you the same answer when you take k equals 1 or k equals 2 as those previous other questions. Other questions? Yep.
Are we going to learn how to rigorously prove that solution 1 divided by 1?
Why do you think that's the solution?
That would be like the optimal case.
Yeah. So to rigorously prove that, you would have to describe a schedule of where a schedule is a series of 5 tuples of drugs in which you've covered all 21 choose 3 things. Not clear to me that that exists even for where the size is 21 choose 3 divided by 10. I mean, the only sort of way to show that such a thing exists is to describe it, either compactly or through some algorithm, or just a big list. And you're welcome to try and use your favorite scripting language to solve this problem. Come up with the best solution you can. Okay, so today is going to be not so much teaching you a bunch of new things, but taking a step back. We've seen a bunch of different techniques for counting and some theorems. So we'll try and use them a bit. And one of the things I'll tell you now you'll learn today is useful for question 4.4 on the assignment, which many of you are struggling with. And it's one of those questions that if you view it the right way, it becomes easy, but there's also a long, complicated solution as well. So if you don't see the easy solution, then you're stuck doing the long, complicated sort of case analysis. All right, so I want to come back to this Pascal's triangle, which is basically just a list of binomial coefficients, row by row, where row R, for example, row 2 here, gives you all the binomial coefficients with 2 on top. So 2 choose 0, 2 choose 1, and 2 choose 2. 3 choose 0, 3 choose 1, 3 choose 3, 2, 3 choose 3 in the third row, and so on. So this thing is called Pascal's triangle. And you usually draw it offset like this because you keep having, an odd number of entries, and then an even number of entries, and an odd number of entries, and an even number of entries, and you kind of write them offset like this. So here it is in this sort of binomial form with using this binomial coefficient notation. But here's the same thing with actual numbers. So number of ways of choosing 0 things from a set of size 0 is 1. In fact, the number of ways of choosing 0 things from a set of any size is 1. That's where these 1s are coming from. And similarly, the number of ways of choosing k things from a set of size k is also 1. You have to take the whole set. And then the numbers in the middle kind of wiggle around. All right. So we saw a few things about binomial coefficients last class. So one of them is maybe this Newton's binomial theorem, which explains why these are called binomial coefficients. And it says that x plus y to the n is equal in terms of this thing here. Well, for example, it tells us that if I look at x plus y to the 6, so the coefficients in the sum all come with an n on top, so n is 6 in this example, and it runs through all the values of n choose k. So that tells us that, well, 6 choose 0 is 1, there it is, so we get 1 times x to the 6 no y, plus 6 times x to the 5y plus 15, x to the 4, y squared, plus 20, x cubed, y cubed, plus 15, x squared, y to the 4, plus 6, x to the x, y to the 5, plus y to the 6. So the coefficients of one of these binomial things, they just come off this row. So x plus y to the n, you read the coefficients of that off of the nth row of this triangle. So that's where that comes from. So here's something interesting. An identity for binomials. It says if I take the sum k equals 0 to n of n choose k, that is equal to 2 to the power n. And that looks really strange, right? Because this is 2 to the n is a really simple formula. But if you look at these things, these have n factorials in them and k factorials and n minus k factorials, now ranging over all the values of k between 0 and n. And somehow that all cleans up nicely to 2 to the n. So what does that mean? Well, that means that if I take the nth row of this triangle and add up all of the values that I see here, I'll get 2 to the n. So for example, here's row 3, and 1 plus 3 is 4. Now we're at 7. Now we're at 8. Indeed, 8 is 2 to the power 3. Let's check it here. Here's 5. 5, 11, 15, 16. Indeed, 16 is 2 to the power 4. So it looks like it's true. How would you prove this? Anybody know how one could prove this thing? So here's a short proof that's not very illuminating. So 2 to the n, let's do something really simple, is 1 plus 1 to the n, right? 1 plus 1 equals 2, right? Okay. 1 plus 1 to the n. Is there something on the board that lets us handle things like this? Newton tells us how to do this, not just for 1 plus 1 to the n, but for any x and any y. So let's try it on 1 plus 1. It's equal to the sum, k equals 0 to n. So we have n choose k. And then we have a 1 to the n minus k, but 1 to any power is just 1, right? And we have a y to the k, but y to any power is just 1. So, I mean, this is times 1 to the n minus k, times 1 to the k, but these are irrelevant. So that's it, there's the proof. Everyone sees that? So the only sort of leap here is we use Newton to get from this side to this side. But there is another more illuminating proof of this. which is the following. Let's say S is a set of size n, and let's say A is the set of all subsets of S. So this also has the name. This is called the power set of S. We've studied these before. How big was the set A? S is an n-element set. How many subsets does it have? What's that? Louder? 2 to the n. Yep. So it has size 2 to the n, and we proved that, I don't know, last class or the class before, I don't remember, but there's an easy way to see it, which is just list out the elements of A one at a time, or it's not the elements of A, the elements of S one at a time, and you have to decide for each element, is it in the subset or is it not in the subset? So there are n elements in S. For each one we have a choice to make where there's 2 options. We put it in the subset or we don't. Therefore you can generate 2 to the n different subsets this way. Okay. So that's one thing. But now so we're going to use this double counting trick. So we figured out that size A has size 2 to the n. But let's think of it another way. Let's say for each I in, or each k even, k in 0 up to n, let ak be the number of subsets of S, or let AK be actually the sets themselves, a set of subsets of S of size exactly K. Okay, so now I'll fix some value K, maybe K equals 3, and say, well, what if I'm only interested in the sets of size 3, the subsets of S that have size 3. So how many subsets of S, an n-element set, how many subsets of size K does it have? So I have n elements, an n-element set. I'm looking for subset of size K. How many subsets of size K of an n-element set are there? Yep. N choose K. By definition, remember the definition of n choose K is it's the number of K-element subsets from a set of size n. So by definition, the size of this thing is n choose K. But now wait a minute. A, which is all the possible subsets of S, well, that consists of all the sets that have 0 elements, and all the sets that have 1 element, and all the sets that have 2 elements, and all the sets that have so on, all the way up to all the sets that have n elements in them. If I'm interested in all the possible subsets of S, well, some of them have 0 elements, some of them have 1, some of them have 2, some of them have 3, some of them have n. And that means that the size of A, now this thing contains only sets of size 0, this thing contains only sets of size 1, this thing contains only sets of size 2, this one contains only sets of size 3, and so on. That means they're disjoint. Right? A set of size 1 is not also a set of size 2, so these are definitely disjoint things. And so we can use the sum rule to get that the size of A is just the size of A0 plus the size of A1 plus the size of A2, and so on, up to AN. But wait a minute. That says that the size of A is size of A0 is n choose 0. Size of A1 is n choose 1. That's what we have over there. N choose 2, and so on, n choose n. That's just the sum, k running from 0 to n of n choose k. So we have this set A, which is the power set of S, a set of size n. We determined from previously that the size of A is 2 to the n. And now we've just shown, well, not only is the size of A 2 to the n, but it's also the sum k equals 0 to n of n choose k. If both of these things are equal to the size of A, then they must be equal to each other. So there's a second proof of this identity, that 2 to the n is k equals 0 to n of n choose k. So that's telling us that in this triangle here, you take any row and you add up the values, and you'll get 2 to the row number. Looks surprising. You've just quickly inspected this thing. You have no reason to believe that, a priori, that this thing is 2 to the power 6. I'm just looking at this row. Why is this 2 to the 6? It's not at all obvious until you add them up and realize that it's 64, but you didn't see that. Didn't see that coming. The way to remember it is just to remember that if I want to list out all of the subsets of an n-element set, I can list the 0-element subsets, the 1-element subsets, the 2-element subsets, the 3-element subsets, and so on. I'll get eventually all of the subsets, and that explains why you have this identity. So I'm seeing some confused faces. Is that because?
What does it mean by 2 to the power of n for this triangle thing?
By 2 to the power of n, I mean 2 times 2 times 2 times 2 times 2 n times. Okay. Is this clear? Or should I have stopped at the first proof? That proof there. Okay, good. If I want to know the entry in the n plus 1th row of this thing, the kth entry in the n plus 1th row of Pascal's triangle, I can get it by taking the k and the k minus 1th entry of the row just above. And in this picture, you can see that happening everywhere. Where did this number 4 come from? It's 3 plus 1. Where did this number 10 come from? It's 6 plus 4. All right. Where did this 15 come from? It's 10 plus 5. This is row n plus 1. This is row n. There's the k minus 1th entry, and there's the kth entry. So this one is easy to remember if you have this picture in your head at all, because that's how you use Pascal's sort of little theorem to to draw this thing. I don't memorize the entries in this thing. I just draw one row at a time and get the next row by looking up at the previous row. And there's a generalization of that that is Vandermon's theorem. So Pascal looks at n plus 1, choose k. Vandermond looks at n plus m, choose r. And whereas Pascal only has somehow these two things, Vandermond gets the sum, k equals 0 to r of m choose k times n choose r minus k. And you may remember that the reason that that's happening is because we have this big set of size n plus m over here on the left. That's what this represents. We want to choose r elements from it. And if we look at how we can do that, well, we can color that set in two colors. One color has size m, the other one has size n. And whenever we take r elements from this set, well, some number, let's say k of them, are on this side, and some other number, r minus k, are on this side. If we take a total of r elements, then the number on this side plus the number of this side adds up to r, and that's basically the proof of this theorem. You split the sets depending on how many elements of this these m that they have or not. But from Vandermond, you get another interesting identity. Which is if I take the sum, k equals 0 to n of n choose k squared, then I actually get 2n choose n. Now that looks crazy. Now I've got this thing, which is a bunch of binomial coefficients, only running from, where k is running from 0 to n. So these are all things that have an n factorial on top and n minus k factorial on the bottom, k and a k factorial on the bottom. And somehow I add all those up and I end up with this binomial coefficient that is 2n choose n. I have to square them all. So what is that? What does that look like in this picture? Well, that says that if I take, for example, row 3 here, and I look at 1 squared plus 3 squared plus 3 squared plus 1 squared. So what's that? 1 plus 9 plus 9 plus 1, that's 20. Now, on the right-hand side, I should go, if I was at row n, I should go to row 2n, and I should go right in the middle of that row. And I'll get the same number. A really surprising result. How do you prove such a thing? Well, actually, it's not hard because this is just a special case of Vandermond. So let's look at, use Vandermond's theorem with n equal to m equal to r. So everywhere we see in this theorem an m, an n, or an r, we're going to replace it with n. So that says that m plus n, choose n, is equal to the sum k equals 0 to n of n choose k, n choose n minus k, what can you tell me about n choose k and n choose n minus k? So for example, 6 choose 1 and 6 choose 5. Yep. It's the same number. So we actually saw that as well, this sort of little theorem, n choose k is equal to n choose n minus k, because if I want to give you a subset that contains k elements, I can either tell you what those k elements are, or I can tell you the n minus k elements that are not in the subset. Right? So every time you give me a set of n minus k elements, if I take those away and leave the others behind, then I'm left with k. So there's a bijection between these two things. And that shows up as a symmetry in this triangle. Right? In the middle, there's the central row that everything appears only once, but it's mirrored on either side of that. So that says that this thing, n choose n minus k, is the same thing as n choose k. So this is the sum of n choose k squared, which is what we're trying to prove. The sum of n choose k squared is equal to 2n choose n. So really strange and interesting behavior comes out of this triangle. Right? Do it for 2. This is 1 plus 2 squared is 4. We're up to 5. We're up to 6. So we should look then in row 4 in the middle. There's 6. Okay. So sort of neat things to do with Pascal's triangle, and a few sort of different simple proofs of those things. So, any questions before we move on? Yeah. How did I decide to set those things? Because I know what I wanted to prove. But if I, it's not really how did I decide to set those things. That, in fact, it more goes the other way, or the way these things get discovered is more the other way around. You prove this Vandermonde thing, and you say, wow, this is complicated. I have an N, an M, and an R. What happens if I make them all the same? And if you do that, you make them all the same, you get this thing, which immediately gives you this thing. And if you've done this, worked with binomial coefficients at all, you realize these two are the same. And you realize, wow, I've got a really cool identity. That has a sum of n choose k squareds and a 2n choose n over here. So, I mean, the way that this is most likely discovered is the more complicated general thing was discovered first, and then you notice that if you set all the values to be equal to n, you get something that's clean and tidy like this. If I just showed you this, and you have not seen any of these other things recently, this would be, not easy to prove. It would take some real insight. You'd have to probably rediscover a bunch of things about binomial coefficients, ultimately leading to Vandermonde. So So I've said it before, most of the stuff we do in this course, every individual step is easy. The rules that we have for doing things, product rule, sum rule, complement rule, all of those are simple and easy to understand. Where the magic happens is just the clever use of those things. And this is, one such example. So questions before we move on? All right. So, let's tackle a couple of counting problems. Here's the question. How many distinct reorderings of the word success are there? Okay, and there's a reason that I used reorderings here. So by reordering, I mean you just take the letters and you put them in a different order. And, well, we have a name for that already, that kind of operation of taking things and putting them in a different order. We usually call it a permutation. The reason that I don't want to say permutation here is because if I was counting permutations, you would know the answer would be what? How many permutations of 7 elements are there?
7 factorial.
7 factorial. So that would be the answer if I was really counting permutations. And so, for example, when I count permutations, let's say of 1 through 7, then one of the permutations that I count is 1, 2, 3, 4, 5, 6, 7. Another permutation that I would count is 7, 2, 3, 4, 5, 1, 6. So if I use this permutation to rearrange the letters of this word, well, this is the identity permutation. So letter 1 goes to here, letter 2 goes to here, 3 goes to here, 4 goes to here, 5 goes to here, 6 goes to here, and 7 goes to here. Or if I use this permutation, so that is 7 goes to here, 2 goes to here, 3 goes to here, 4 goes to, 3 goes to here, 4 goes to here, 5 goes to here, 1 goes over here, and 6 goes over here. Well, look what happens. 2 different permutations, but I actually get the same word. So 7 factorial won't be the answer because when I count permutations, this is treated differently than this, but actually rearranging those letters these 2 different ways actually gives me the same word again.
What's the answer then if it's not 7 factorial 7?
Okay, so the question is, what's the answer? Let's figure it out. So, the answer is not 7 factorial. And this is why, it's because of questions like this that I don't like to use, I don't use the terms permutations, combinations, because people like to sort of blindly apply those things. What I prefer is that they understand how to get those things from basic principles, like product rule. Because really there's only a few things where the answer is n factorial and some other things where the answer is n choose k. For everything else, you have to work it out from first principles. So let's go back to our old friend, the product rule. And just try and write a procedure that's going to give us some rearrangement of this string. So I have a procedure that's going to take, let's say, a bag of letters. So I have 3 S's. 1, 2, 3. I have 1 U. I have 2 C's. And I have 1 E. Those are the letters I have to work with, right? This is like a Scrabble hand. So I would like to write a procedure that will generate me some ordering of these things. Let's 2, 3, 4, 5, 6, 7. In fact, this is really Scrabble. Scrabble, you have 7 letters. You lay them out on your little wooden stick. How many different ways can you do this if these are the letters that you're given? So how can we tackle this? In a way that's amenable to the product rule.
You pick the first letter.
So one strategy is to say, well, let's pick the letter that we're going to put here. How many choices do we have for that?
7. That's already letter 1. Yeah, 4.
There's 4 choices. Now, the problem with that strategy is that if I decide that the first letter that I put here is an E, then I'm out of E's, and I only have 3 choices. On the other hand, if I decide that the first letter that I put here is an S, then I still have 4 choices. And to use the product rule, what we always want is that at step I, we have n sub I choices no matter what we did before. And this breaks that because at step 2, we may have 3 choices or we may have 4 choices depending on what we did at step 1. Yep?
For S, we choose 3 positions from 7 to 4.
Yeah. So, first thing we do is we choose 3 positions for S. Right? So I come along here and I pick 2, 5, and 6, for example, and say that's where my S's are going to go. Now, how many different ways do I have to do that?
Pick 3 out of 7.
You get to choose from 7 positions, you choose 3 of them. So what do you think step 2 is? Yeah. So step 2 is choose 1 position for U. How many ways are there to do that? Well, 3 of the positions are already occupied by S's, so there's 1, 2, 3, 4 ways to do that second step. 4 choose 1, which is 4. All right, what do you think step 3 is?
Wait, how's it 4 choose 1?
4 choose 1 is just means pick 1 position from 4.
Oh, okay, yeah, there are 4 positions left and you have to pick 1. Okay, that makes sense.
Yeah. So what's step 3 then? Yep.
Choose 2 positions for C.
Choose 2 positions for C, and how many ways are there to do that?
Pick 2 out of 3.
So right now, if we place the u, let's do that, like we did in step 2. What's left? There's 1, 2, 3 places left, and I have 2 c's to put in there. So that's going to be 3, choose 2. Let's place those. Maybe we do C and C. What's step 4? Yep. Step 4, choose one position for E. There's only one position left here, so that's 1, choose 1. So there's our procedure for creating one of these things. It has 4 steps. First step has 7, choose 3 options. Second step has 4, choose 1. Third one has 3, choose 2. And the last one has 1, choose 1.
Wait, how's it 1 choose 1?
So 1, choose 1 is how many subsets of size 1 are there of a 1-element set? There's exactly 1 subset of size 1 of a 1-element set, right? As we said here, there was 1 empty position. Somebody says, pick an empty position. There's exactly 1 way to do that. Okay, so now we can be a bit more precise with our answer. It is 7, choose 3. 4, choose 1. Times 4, choose 1. Times 3, choose 2. And remember, we have explicit formulas for all of these things, right? This is 7 factorial over 3 factorial, 4 factorial, 4 factorial over 3 factorial, 1 factorial, and so on. We can plug all of this in, and I think we get 420. Or maybe that's just wishful thinking on my part. No, it's 420. So there's the answer, which is not 7 factorial. Okay. So, questions? Yeah?
Can you also do something like, because there's 7 words, so 7 factorial, and then since there's 3 S's and 2 C's, you divide 7 factorial by 3 factorial times 2 factorial?
Yeah. So, again, if you tear this thing apart and write it explicitly, what you'll find is that this is actually 7 factorial divided by 3 factorial, 2 factorial, 1 factorial, 1 factorial. So why is that? That's another way to tackle these problems, which is actually by saying, list out all 7 factorial permutations, but then count how many different permutations take you on to the same thing. So for every, and what we'll find is actually, this is the number. If I were to list out all of the 7 factorial permutations, I'd see the same word appearing many times. How many times would I see a word appearing? Every word would appear exactly 3 factorial times 2 factorial times. I'm not, so this is typically the view that you call factoring out symmetries. I'm not a big fan of it because you have to be quite careful to make sure that everything appears exactly the same number of times. In this case, it's a fairly easy argument, but more in some other cases, it's not not obvious. In some other cases, it's not even true. But you know, so you can. This is a sort of a formula, and especially this here is a formula for tackling problems where you're interested in all permutations, except some of the elements aren't distinct. Some of the elements appear more than once. Yep.
I have a question. Where did you get the denominator when you were dividing factorial 7?
Here?
Yeah, where did you get all those numbers from?
Okay, so the reason that I'm getting this 3 factorial and the 2 factorial is that rather S occurs 3 times. So a way to think of that is, well, for example, we saw it happen here. Here we had 2 permutations that gave us the same word. And the reason that that happened is because if I just look at where the S's went, right, they went to these positions. Here, 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 here. But they did that through different permutations of those 3 elements. And actually, if you look, there would be 3 factorial ways of doing that while leaving the C's this way. And then there's another 2 factorial. Multiply that by 2 factorial for the ways of organizing this. That's why I don't like to work with this so much, because I think it's more confusing than the step-by-step approach. Question there? So, let's try something completely different then. Here is a formula. x1 plus x2 plus x3 is equal to 11. How many solutions? Does this have? 0 and our integers. Anybody guess? Doesn't look like anything we've seen can tackle this kind of thing, right? We could try the product rule, but what would we do? Choose the value of x1 first, then choose the value of x2, then choose the value of x3. We try to work through that, we realize it fails right away, because if I choose x1 equals 0, then x2 could be anything between 0 and 11, right? But if I choose x1 equals 11, then x2 has to be 0. So, and then the product rule, the number of choices we have at the second step should not depend on the choice that we made on the first step. And that already fails here on the second step. So there's the question. Here's the answer. 13, choose 2.
How did you know?
How did I know? Now that you know the answer, does anybody see why that's the case? Yep.
You can make a trend that have 13 boxes, and 2 of them are like black boxes. Those 2 black boxes divide these 13 boxes into 3 parts.
Wonderful.
X1 is x3.
Exactly. So let's draw a picture. So, there's a few ways to think about this, but the proof is, I'll write the idea here and then we'll sketch it there. With the bijection between solutions. So what does that mean? We have a set A of solutions. These are triples, x1, x2, x3, such that x1 plus x2 plus x3 equals 11, and x1, x2, x3 are all bigger than or equal to 0. Are integers. Right? So that's what we're trying to count. How big is this set A of solutions? And bit strings of length 13 with exactly 2 ones. So the set B is that bit strings of length 13 sounds complicated, but as soon as you see the example, it'll be obvious. So here are the 13 digits of a bit string, say. And I'm interested in a bit string with 2 ones. So for example, maybe a 1 here and a 1 here. So somehow I want to relate that and zeros everywhere else. I'll hardly draw those in because they're not actually that important. So can someone tell me how to interpret this bit string as values of x1, x2, and x3? Not you, because you know the answer. Yeah? Yeah. So these 2 ones here, they break this thing up into 3 pieces. The stuff before the first one, the stuff after the first one but before the second one, and the stuff after the second one. So that's 3 things. So before the first one, there's 2 zeros. So x1, let's say that's 2. For here, there's between the first and second one, there's 1, 2, 3, 4, 5, 6 zeros. So x2 is 6. And after the second one, there's 1, 2, 3 of these things. x3 is 1. What did I do wrong? 3. X3 is 3. Wow. That was spectacularly bad counting. So x3 is 3. All right. So do these add up to 11? They do now. Do they only add up to 11 because I picked the one here and the one here? No. Why do these add up to 11? They add up to 11 because there's 13 slots here. 2 of those slots are occupied by 1s, and the other slots are all zeros, so the other 11 slots are zeros, and x1 plus x2 plus x3 is just the number of zeros in this string. So it's always going to add up to 11, no matter where I put the 1s. Yep.
So the idea of this is just break this the string into 3 different parts.
Yep.
And because you have to break into different parts, you don't want to take the slots that's already there, so you insert.
Yeah. So I mean, the idea is that if I have a stick and I cut it in 2 places, then I'll have 3 sticks.
So let's say if you have an x4 in there, your answer will be 14.3.
It would be 14.3, yes.
Okay.
We'll see the general theorem in a second. Okay? All right. So let's be, we have a little bit of time, so let's be precise. We're supposed to define a bijection between the solutions in A and the bit strings in B. So that bijection looks like this. If you give me a solution for A, x1, x2, x3, that's going to take me onto this string, which has x1 zeros, then it has a 1, and then it has x2 zeros, and then it has a 1, and then it has x3 zeros. So the claim is that f from the set of solutions onto the set of binary strings of length 13 with exactly 2 1s, that's a bijection. So first of all, if I give you x1, x2, x3 that add up to 11, do I get something in B? Let's check. So to be in B, I have to be a binary string. Yes, looks like I'm only making binary strings. I have to have exactly 2 1s. Yep, everything is zeros except for these 2 1s. And my length has to be 13. Why is the length 13? Well, it's 13 because x1 plus x2 plus x3 is 11. So this string has 11 zeros plus the 2 1s means it has length 13. So definitely f is a function from A to B. Is it a bijection? Well, to be a bijection, we have to be 1 to 1. So what does that mean? 1 to 1 means that if I look at something in B, there should be at most one thing in A that goes onto it. So I should not have 2 different things in A that go onto it. But if I look at something in B, that thing in B is a string that looks like this. 2 1s, everything else zeros. What is the thing in A that goes on to this string in B? Well, we just figured out that there's only one, and you get it exactly this way. Count the number of zeros up to the first one, that's the value of x1. Count the number of zeros between the first and second one, that's the value of x2. Count the trailing zeros, that's the value of x3. And if I give you different values of x1, x2, or x3, I'm not going to get the same string again, because the ones will be in different places somewhere. So it's 1 to 1, and actually the same thing shows that it's onto. What does onto mean? Onto means that everything in B has something going into it. So there's no lonely thing over here with nothing in A that maps onto it. But we saw that because this already, take anything in B, looks like this. It's a string of zeros and ones of length 13 with 2 ones. Count the number of leading zeros, count the number of zeros between the 2 ones, count the number of zeros, trailing zeros. That gives you something in A that maps to it. So indeed, there is a bijection from A to B. So by the bijection rule, the size of A equals the size of B. And actually, the first application of the bijection rule that we saw was exactly this: how to count the number of bit strings of length n with exactly k ones. That's just n choose k. Or in this case, 13 choose 2. I mean, there's the proof. Choose the locations for the 2 ones.
So it is 1-to-1.
It's 1-to-1 and it's onto, so there's a bijection between these things.
Onto is where you leave something out, or it is
Onto is that you should never leave anything out of B. So everything in B should be hit by something in A, and 1-to-1 means everything in B should be hit by at most one thing in A. Yep.
You could just as easily have set your set B to the bit strings of length 13 with exactly 2 zeros, right? And it would have gotten you the same.
Yeah, then you just reverse the roles of zeros and
Because I'm
ones.
just thinking like maybe it would be easier to see that way because like you can then take your original 11 and then make it thin into like 1 plus 1 plus 1 plus 1 plus 0. Like it would look easier in the equation.
Well, I don't know. I mean, alternating the roles of zeros and ones, I think in the string doesn't matter too much. But when you do that, you're again applying this symmetry, right? Okay. So I think maybe we see that this isn't, the numbers 11 here and 3 here are not magical, right? Like, I could change 11 to 15. What would the answer be? (17) choose 2. And what if I added another variable x4 here? 14 choose 3. Yeah. So let's write down the general statement of this thing. The proof is exactly the same.
I have a question. If you had x4 equals 11, not e14, choose 3?
If you had the sum of x1, x2, x3, and x4 equal to 11, then you add 3 here, so that's 14, choose 3. Yep. Here's the general theorem for any integers k bigger than or equal to 1 and bigger than or equal to 0. The number of solutions of x1 plus x2 plus x3 up to xk equals n, where x1 to xk bigger than or equal to 0 are integers, is n plus k minus 1, choose k minus 1. And the proof is exactly what we just saw. We look at this, let's say, bit string of length n plus k minus 1. We pick k minus 1 locations to put 1s. And that gives us k values for the variables x1, x2, up to xk. Always important to remember that if I have a stick and I break that stick k times, the number of pieces that I get is k plus 1. In this case, I break the stick k minus 1 times, and I get k pieces. Is that clear?
So k minus 1 is for everything, n minus k plus 1?
K minus 1 is just the number of locations that you choose for the ones in this bit string of length n plus k minus 1.
Okay.
We had n equals 11, k equals 3 was our example.
Okay, so number of spots.
Yeah. All right. Let's try something much, much harder. Same question, but I add one line. So now, I don't just want x1, x2 solutions where x1, x2, x3 adds up to 11, but I'm happy if they add up to anything less than or equal to 11. So there's a long way and a short way to do this. So can anyone tell me the long way? Without, yeah? Yeah. Yeah. So if they add up to less than or equal to 11, then either they add up to 0, or they add up to 1, or they add up to 2, or they add up to 3, and so on, all the way up to 11. And this thing here actually tells me what the formula is for any value of n. So I can just add up the value of this thing. K is always equal to 2, and n is 0 plus 1, n is 1, n is 2, n is 3, up to 11. You get a long formula, and maybe a big number pops out at the end. That's the hard way to do it, or the long way to do it. Maybe I'll tell you the answer. So if you did the long way, then what you wouldn't see is that the answer is actually (14) choose 3. Now that you know the answer, do you see how to prove it? Tell me what I should do next.
So 3 sticks in here.
Put 3 ones in here. Well, if I put 3 ones in here, I get 1, 2, 3, 4 intervals. What do those 4 intervals add up to? 2, 3, 4, 2. What does that add up to? 11. What do the first 3 intervals add up to? They add up to 9. And in general, what can you tell me about what those first 3 intervals add up to? Not more than 11. So I have x1, x2, x3. For this particular string, I would say x1 equals 2, x2 equals 3, x3 equals 4. Those are 3 integers. They're all bigger than or equal to 0, and they add up to something that is less than or equal to 11. And now, just go back and do exactly what we did before, and notice that actually every time I drop 3 ones into a string of length 14 like this, the first 3 intervals add up to less than or equal to 11. And then there's some leftover, which counts how much less than 11 the first 3 add up to. Now just check. If you give me x1, x2, x3 that add up to less than 11, I drop x, make some zeros, put x1, make some zeros, put x2, make some zeros, put x3, and then put a 1, and then finish off with exactly the right number of zeros to make the whole string of length 14. So this number of zeros here is, what would it be? I guess it's 11 minus x1 plus minus x2 minus x3. That's the whole proof. So the answer is 14 choose 3 because there's a bijection between solutions to this and strings, binary strings of length 14 with exactly 3 ones in them. And the more general theorem is, okay, same statement, except we want less than or equal to n. And instead of choosing k minus 1 things, we go ahead, well, instead of n plus k minus 1, it's n plus k, leaving n not chosen, and so we choose k. Hardly changes at all. Okay. And now, a little brain teaser. Really useful brain teaser, so pay attention. What if I restrict you that in this string, you don't want to have 2 ones right beside each other? Or another way to think of it is the values of x1, x2, and x3 should not be bigger than or equal to 0, but maybe they should be bigger than or equal to 1. Something like that. So use that as guidance when you get stuck on question 4.4 of the assignment. And that's a good place to stop for today.